Hello, everybody. I just wanted to go through these Bernoulli problems one more time. I know there is some confusion in class, and I just worked through them, so I want to go through again just how to do it with a little bit more smoother approach. So right here, we went over this problem where the fluid is flowing into the tank, and it is assumed that it is flowing out at the same flow rate. So some of the assumptions that are made in this problem is that this height level is going to remain constant. So that means the QV here must be equal to the QV here, so the volumetric flow rate. So since things are moving, it's going to be helpful to start with the Bernoulli's equation as well as defining where is your 1, where is your 2, and where is your origin. So what I'm going to say right here is I'm going to say right here is my point 1, and then right here is my point 2. Also going to be somewhat important is to define your origin. So what I'm going to say is I'm going to say right here is where y equals 0. That's my origin. So now let's do the Bernoulli's equation. So 1 half rho v1 squared p1 plus rho g h1 equals 1 half rho v2 squared plus p2 plus rho g h2. Okay, so and then you just go through and knock them off one at a time. So V1, since this is an open tank, and it's another assumption is that the area here is smaller compared to the area here, such that this V1 is equal to 0. So that means this term can go away. So what you're saying is that the velocity at which, the speed at which this level is changing is small enough to be considered insignificant. So that's what we're saying here with that, which happens when the area of the open tank is significantly larger than the area that's being drained out. So that's going to go to 0. P1, we're right here, that's going to be PATM plus rho GH. So this is at H. So this point that you're analyzing is some H distance away from the origin that you defined. So that is going to be rho GH equals V2, 1 half rho V2. This is coming out at some velocity, V2, so that's not 0. Plus our P2, we're going to assume that it's open to the atmosphere, that it's not connected to another pipe. So we're going to say that just right here at this point, P2 is equal to PATM because it's open to the atmosphere. So right here we have PATM plus, according to our origin, point 2 is at y equals 0, so this term goes away. So we don't have anything else. Okay, PATMs cancel, and what you get left with is 1 half rho V2 squared is equal to rho GH. Rho's cancel, and what you're left with is H is equal to 1 half V2 squared divided by G. Now here's where you need to figure out what V2 is. That is going to come from a part of the continuity equation where we're going to say, not really the continuity equation, but you know that volumetric flow rate is equal to the velocity times the area. So this would be V2 times A2. So we're given this the velocity flow rate. This is also what they're defining as QV. We're given that, and we're also given the area. So what we need to do is say V2 is equal to our volumetric flow rate over our area, and then plug that in. So once we plug that in over here, it's equal to this term gets squared over G. So I did solve it. I believe it's 1.667 is QV. QV is equal to, I believe, 1.66 times 10 to the negative third. Our area, and this is going to be in meters cubed per second because it's given in a minute. Once you convert the area, that's equal to 1 times 10 to the negative 3 meters squared for the area of the outlet. That's A2. So once you do that, you get this term is essentially 1.667 times 10 to the third negative over 1 times 10 to the negative third. Quantity gets squared. and you have this 2 times 9.81 term. That's going to end up giving you that the height is equal to, it does give you something similar to the answer, which is 0.141 meters. This essentially cancels, so if you plug that into your calculator, you should get the correct answer. So actually, what happens here is this will cancel with this times 10 to the negative third, and so when you work out the math, it should give you a good answer. So it's essentially just going to be 1.667 squared over about 20. And that'll give you, yeah, something close to this number right here. Now notice the number is correct here. That's the correct value. However, this is not correct. You need to have this term be squared in order for it to give you the correct answer. So the numerical value is correct, however, the actual work is not. Because if you don't square it, you'll get a very different answer. Okay? All right, I hope that made sense. Now let's move on to the other one that we discussed in class. This one, I think, is also a little bit incorrect, but let's just go through it step by step. Okay, so what we have here is we have water flowing through. So you're seeing that it's flowing through, and that the volumetric flow rate is, well, first of all, the continuity equation says that the mass flow rate of 1 has to equal the mass flow rate of 2 if there's no reaction or accumulation. And mass flow rate is just volumetric flow rate times density. But if the density doesn't change, which in this case it's not being heated up or anything, and the densities cancel, and then you can assume that the volumetric flow rates are identical. So V1, volumetric flow rate 1 is volumetric flow rate 2. Okay, so let's just label our diagram. We're assuming that this is our point 1 because it's giving us a pressure value of 1, and this is our point 2 pressure value of 2. Defining our origin, I'm going to say that this right here is our origin. That's where our y equals 0. Okay, so going back, let's do the Bernoulli's equation. Okay, so just writing it out. If you want to use the other method, which I believe is just 1/2, so V1 squared minus V2 squared plus P1 minus P2 plus rho G H1 minus H2. You can go that way too. If it's 2 minus 1, 2 minus 1, or 1 minus 2, it'll be okay, just as long as you're keeping track of where your variable is at and where you're looking at on the problem. So let's do this equation here because I think that's how it's in the notes. So we know that we're going to have a V1 and we're going to have a V2. So we're going to have that, we're going to have that, we can't cancel out. We're also given a P1 and a P2, so we're going to need that as well. So we can't cancel out anything from there. But here's where we can cancel something out. So our H1 is our height at point 1, which our point 1 is defined as up here, so that does have a height. That's going to be the 0.8. So our H1 has to stay there. Our H2 is where we defined it to be 0, so that's going to go there. So what we have is 1/2 rho, all this term. And I'm just going to make that rho GH equals 0. So let's kind of go back. The question was asking for the volumetric flow rate. So kind of where we started off, our volumetric flow rate, we know that V1, volumetric flow rate at all throughout this pipe is going to be the same. So we can say the volumetric flow rate at point 1 is either, or just in general, since it's going to be the same, is equal to the velocity at point 1 times the area at 1, which is also equal to the velocity at 2 times the area at 2. Now we have all these areas, but we do not have the velocity, so we can't figure out the volumetric flow rate. So that's why we started off with the Bernoulli equation, and that's where we need to go. We need to figure out either V1 or V2. Now we have all of these. We have our H, gravity, density, P1, P2. We have our rho. We just don't have V1 or V2. However, we can form a relation with them. So we have one equation, two unknowns, but then we just have this equation right here to establish one equation with one unknown. So you can go ahead and pick one, whichever one you want. I guess I'll just say V1 is equal to V2 times A2 over A1. This should be A1. Okay? So now what I'm going to do then is just take this thing right here and plug it in right here. Okay, so when I do that, I'll then have an equation with one unknown. So what I'm also going to do is I'm going to simultaneously take this term to the other side and take this term to the other side. So I'm going to get 1/2 rho. This ends up being V2 A2 over A1. All that squared minus V2 squared. It goes to the other side. So I can either say it's P2 minus P1 minus rho GH. And then again, I just swap the signs here, and that pops out the negative. So we're arranging now, moving the rho and the 2 over, we get V2 that squared 2 times P2 minus 1 over rho minus 2GH, because the rows are going to end up canceling. Okay, now it's just algebra, factoring out the V2 squared. So all this stuff, and then I'm going to say V2 squared is equal to this 2 times P2 minus P1 over rho minus 2GH all over this A2 over 1 minus 1. And then finally I'm going to say all this stuff is just taken to the 1/2. Okay, not too bad. So everything here is given, so you say that your V2 then must be equal to 2 times, what is P2? P2 is 1.2 and P1 is 1.6. 4,000, because it's given that it's water. The height, I believe, is 0.8. All that over, so the ratio of the areas, it's going to be just related to the diameter squared, because you can just say pi over 4 diameter 1 over pi over 4 diameter 1. So this is squared though. So that's the area of the top one, the area of area 1. Area 2 is going to be the exact same, but this diameter squared. So it's just going to be diameter 2 squared over diameter 1 squared, all of that squared. So that ends up just becoming diameter 2, 100 squared over 200 squared. All of that is squared. I'm leaving it in millimeters because it's just going to end up canceling out if you do unit conversion, so it's not that big of a deal. And that's going to be minus 1. You can also do, okay. So when you figure that out, just plug it into your calculator. You should end up getting, oh, don't forget the square root. When you plug it into your calculator, V2 is approximately equal to about, I don't know, I think like 10 meters per second or something like that. And then the whole point of solving for velocity 2, remember, was so that we can get this volumetric flow rate, this QV. And so we'll just use this is equal to that. So you get, going back, velocity flow rate is equal to, or volumetric flow rate, excuse me, is equal to your velocity times your area 2, which is equal to this, about 10 meters per second, times this. The area is going to be pi over 4. Now you have to actually convert it to meters because the units matter. So that's 100, so it's 0.1 squared. Okay, and you're going to get a value. So one issue that I want to point out is when I calculated it, I got somewhat very close to this, but it was 0.06. 793. So I think there was an issue. I think that it's off by an order of magnitude. If you do get this correct answer and not my answer, please let me know. If there was an error that I worked in here, I don't think I did. But yeah, hopefully that helps out. It's a little bit more clear. I'll work on getting a uh, macroscopic energy balance problem out shortly. Thanks for watching.